So you may ask, why hack network devices? What is it that makes the network device so attractive to an attacker, or maybe even to the defender who is defending against the attacker? And really, when it gets down to the base of it, it's the core of the network, right? This is where all of your packets are flowing through. And really, if you have a way of snooping or injecting packets off the network, you really have a way of controlling the endpoints, even without having to worry about the endpoints themselves necessarily individually, if you have access to the entire network. Another thing is it may not be monitored as closely as your hosts. I mean, we're all very familiar with how we monitor our hosts today. Really, when it comes down to it, though, routers and switches and networking devices may not be monitored that closely. Your firewalls, you probably are monitoring those fairly closely, but routers and switches maybe not as much. They have a longer system life cycle. What does that mean? Well, that means that you don't replace them as often, right? A lot of times, sometimes I've even heard people that just load up the code that it came with, that a switch or a router came with, and that's what it runs for the rest of its life. They don't keep it up to date. They don't patch it. They don't have any malware detection, right? You don't have any antivirus that runs on a switch or on a router to make sure that it is free of any kind of malware. Another issue is that it's antiquated. A lot of the protocols that are on a router or a switch, they're running protocols that were maybe designed back in the 80s. They're IGPs, maybe early 90s. Where the configuration stays static. I can't tell you how many devices I've seen where you have, maybe they have an Excel spreadsheet, right? And you plug in some values in it and it spits out a configuration, and that's what you use. It could be that simple. Routers and switches, they have features such as port mirroring, tunneling, lawful intercept, where you can use those as an attacker to infiltrate and even exfiltrate data. So when I say infiltrate data, you can inject packets that look like they're coming from some host, where in reality they're coming from somewhere completely different. An example of this is like using GRE tunneling. If you can send packets directly to a router, you can have that get stripped off, that GRE tunnel get stripped off and then forward onto a host. And then finally, some devices, they have built-in analysis tools. Especially some of the newer switches and routers, they have Wireshark or T-Shark or something like that built into them, so that you can analyze packets and flows directly on box without having to copy them off and look at them somewhere else. So as far as the steps to owning a network, we'll start out with you have an exploited vulnerability. And this vulnerability could be a compromised credential, could be an unpatched software, the vulnerabilities in the software, and there's just no patch that has been applied to the device. And then other times you'll have 0 days, which are genuine vulnerabilities that have not been discovered and they have not been reported on. And so sometimes you find those. Really what happens, though, more often than not, are compromised credentials. And you're going to see this later on. I'm actually going to show you how to copy off credentials from other protocols like AAA protocols like Radius or TACACS, where you have access to a device and you wait for a legitimate administrator to log into the device, and then you'll get their password, and then you'll be able to use that access to pivot to other devices. And then the second step is once you have access to the device, then you can start doing things like configuration changes. You can start turning on GRE tunnels. You can turn on lawful intercept. And then if you're a lot more capable and you have more resources, you can do things like in-memory network operating system modifications. That's where you could patch the code so that, for instance, you can turn off all kinds of password checking, so that if you log in, you can give any password you want and let you in for a particular account. These are things that you can do. Another thing you can do is, let's say you wanted to make your change persistent. Then you can change the code that's actually on the disk of the network operating system itself, so that when it boots up the next time, you have your change that you've made. Another thing you could do is change the bootloader. So what this applies for is not only for code that has already been installed on the device, but code that could be installed in the future of the device. So you could patch the bootloader so that it goes through your code, and as it boots up, it can change the code to do whatever it is that the attacker wants when the system boots up, so that it comes up and it always comes up in the same state. And then finally, the result, once you have this, you can get persistence. So by doing some of these in memory, on disk, and bootloader modifications, you can have persistence. So even if the device is rebooted, in some cases, if it's reinstalled, you have that access. Another thing that is starting to become a lot more serious is that now when you have access to do things like bootloader modifications, is you can brick the hardware. You could have a very, very expensive device that sometimes costs upwards of hundreds of thousands of dollars, and you can go through every line card that's in that device and just basically modify the bootloader so that it doesn't boot. And then later on, when it gets rebooted, maybe by the attacker or maybe by some kind of maintenance window that has been scheduled, the device goes down and it never comes back up. And then finally, you have data exfiltration, right? You have these features that are built in, such as lawful intercept, and then that copies the data out of the network, in some cases tunnels it over the internet to a system that the attacker controls. So next we're going to talk about the layers of the internet. Sometimes this is called the Open Systems Interconnect Model, or OSI model. What I wanted to show you is that protocols are layered like this for a reason. And when I talk about protocol, what a protocol is its formal rules of communication. Okay, we have the Internet Protocol Suite. It's a whole series of protocols like IP, that's the Internet Protocol. You have the Transport Control Protocol, TCP, or User Datagram Protocol. These are all protocols that run under the IETF. They're all standardized by the Internet Engineering Task Force. That's their umbrella. And then we have these protocols that are arranged in layers. They sometimes call this a stack. But not only is it a stack, they're actually nested like Russian dolls, where you have a doll that's inside of another doll inside of another doll. You have this data that is copied in at, let's say, you have a message. Let's say you're sending from one point to another. That message gets copied into a segment, and then tacked onto that, you have a packet. This is at layer 3. And then at layer 2, you have a frame, and then outside that is layer 1, where you would refer to it as bits. These units of data, as I've already told you, have different names depending on the layer of the OSI that is currently referenced. So that's this part here. You have the message, which is to be segmented. Sometimes you hear this referred to as a datagram if it's not a packet or message that has to be segmented at all. And then down under that, you have packets, frames, and bits. We'll get into this a little further. If you wanted to learn how to remember the different layers of OSI, sometimes I've heard people use mnemonics. And a mnemonic that you can use for OSI is like, please do not throw sausage pizza away. That's if you're going from layer 1 all the way up to layer 7, so you're going from the bottom to the top. If you want to go the other way, if you want to reverse the order, it's all people seem to need data processing. That's how you can kind of remember these. So when we're defining terms, we'll start out with layer 3. Layer 3 routers and layer 2 switches make forwarding decisions based on how to handle those units of data. They call that either packets or frames. When you're referring to packets, you're referring to units of data that are at the layer 3 level. That's the layer 3 encapsulated units of data, which are packets. If you're going down to layer 2 are layer 2 encapsulated units of data. Layer 3 routers, they care about classifying and switching packets based on layer 3 addresses. So that's when we're saying layer 3 encapsulated units of data. They also care a little bit about some of the information in layer 4, such as TCP ports. For instance, you can make what's called an access control list to limit the flow of data from one point of the network to the other. Layer 2 LAN switches, they care about switching based on layer 2 MAC address information. So there are two real models we're talking about. We talk about the Open Systems Interconnect versus the DoD Internet Model. And I'll sometimes be referring to both. The OSI model actually follows the Open Systems Interconnect standard that is defined by the ISO, the International Standards Organization. There was a real set of protocols, a protocol suite called OSI, or it was also called Connectionless Network Services. And that is where this model is based from. They actually had a data link, a network. They had something called CLNP, which was at layer 3, transport layer. They had a multiple layer 4 transports. Then they had session, presentation, and so on all the way through. And then there's another protocol or another model that is also popular called the DoD Internet Model. And this one's a little bit more simplified. And the way the two map to each other is this. The data link and the physical layer, those are more or less get mapped into the network access part, or network's access layer. And then on top of that, you have the internet layer, which corresponds to the network layer. That's at layer 3. Then you have your host-to-host at layer 4, which takes in a little bit of the transport and the session to actually establish a connection from one point to another point in your network. For instance, TCP has to have the three-way handshake, the SYN, SYNAC, and ACK, and that's really kind of a session function. And then above that, you have your process. And some examples of these, let's start from the bottom where we have the network access, our Ethernet or point-to-point protocol. These are protocols that are at more the layer 2, layer 1 in some cases. And then going up, of course, we've got Internet Protocol or Internet Protocol version 6 or IPv6. In host-to-host, we have TCP. That's the Transport Control Protocol or the User Datagram Protocol. And then above that, we have our applications such as HTTP for web pages and serving web pages. And then we have IMAP, which is for mail. This next slide, we're talking about basic forwarding device architecture. Now, whether or not you're talking about a switch, a router, or a firewall, most of the time it is going to be structured just like this. And this may be insightful to you if you're not really familiar with how a router or a switch works. But typically what we have is we have interfaces that come in that are connected to our upstream devices. We have interface outputs that go to our downstream devices. And then in between, we have input queues, output queues, in something called a packet forwarding engine. And this packet forwarding engine could be an ASIC. It could be a software process that runs inside of a router. It could be any of those. And then, so typically it is specialized software and hardware to switch packets in and out of the box as fast as we can. So you have this packet pipeline of packets that go in and go out. And starting up, you usually have a lookup and classify step. And the lookup and classify step, an example of this was VLOOKUP in a routing table, for instance, or what's called the forwarding information base, which we'll get into. You'll typically have some kind of lookup tables that say, if this packet matches against this entry in the table, I'm going to handle it a certain way. I will switch it out this port. I will copy it out multiple ports. In the case if it's multicast, for instance, that's one to many. You can actually copy out multiple ports at the same time. And then the next stage in the packet forwarding pipeline, we have header rewrite. In the case of things like routers strip off all of the information that's at layer 1 and layer 2, and then they look at the information that's in layer 3, and then they rewrite the information in layer 2 and below at each hop. So that's the header rewrite step. And then the step after that, we have to figure out exactly how we want to schedule our packets. We might put our packet into a different output queue on an interface. So there might be multiple output queues on an interface to handle things like quality of service, where you have certain packets that have to be handled with less delay and with better service, so that they have less jitter at the other end when they're received. And that's what we have with the scheduling path. And then finally, we have the path that's really interesting for us hackers, for the hackers that really want to get into the forwarding device, and that is the exception queues. And what that is that when we classify and we look up packets, we have certain classes of packets that are interesting to the software of the device. So in other words, they have to be processed in a different way. Maybe they're the first flow or the first packet in a flow, and those will get punted up to a general purpose CPU. And that general purpose CPU usually runs an operating system. It could be Linux, it could be a special real-time operating system, but these are all on general purpose CPUs using a lot of the same things that you're going to learn, a lot of the same techniques that you've learned. You would access and you would exploit just like you would any host or any end device. And those packets, you also have an inject path. Okay, normally when you have packets that get punted up to the general purpose CPU, the CPU needs to be able to send packets to the network, and that is called the inject path. And then you have these routing protocols, for instance. In the case of a router, switches use something called spanning tree, where they will figure out which ports to block and unblock. But those are all controlled by software, and they're all controlled by a process that pushes down updates to the lookup tables themselves in the forwarding engine. And then finally, and this is typically what I have seen more often than not in most platforms, is that you will have an out-of-band management interface that does not follow any of the normal packet forwarding engine paths. You may have more access through the out-of-band management interface than you normally would have in a data plane interface. In some cases also, we have the packet forwarding engine may be software itself. You may be able to modify that software once you have control of the general purpose CPU. In some cases, the packet forwarding engine may be an exotic architecture, or it may be something fairly common. It may even be x86 that you can actually override and change the packet forwarding engine around. That's sometimes called microcode that runs in the packet forwarding engine. And if you have deep enough knowledge of the system internals, you can change the microcode and actually change how packets are forwarded. So this diagram shows the different layers of communication with the different devices. We start with a client, which has all of the layers of the OSI reference model establishing a communication or connection with a server. The intermediate devices, such as a hub, a switch, or a router, peer with adjacent devices at a given layer. Hubs are physical-only devices. Switches, they peer at data link and physical. And routers peer at both physical data link and the network layer. And then they can also look into layers above for things such as access control lists or network address translation. Note that the physical layer can easily change from electrons over copper to photons over fiber due to layering of the protocol. So in this case, we'll start out with the client. The client will send the frame to a hub, and the hub will just copy that packet out. And let's say we're using copper in this case. And then it goes into a switch, and the switch forwards on based at the data link layer, and we could change our medium completely. We could be copper before, and maybe twisted pair, and then go into a fiber optic connection between the switch and the router. Because our protocols are layered, in that way you could change your physical layer just as easy by just swapping it out and putting in a new physical layer. And then once you get to the packet, to the network level with the router, then you get forwarded onto the switch and then onto the server. And the reason why I wanted to break out the transport versus the application, which is a little bit different, is that typically what happens when you have a process that is sending down to the transport layer, that process will be flow controlled by the layer 4 protocol like TCP. And then finally, I'll be using Viral to build an internetwork, and I will actually show this demo. This configuration is a little more complex than the Viral example you saw back in Lesson 1. We'll build a topology with multiple routers and switches and perform a trace route to see each hop from Kali Linux client to an Ubuntu server. We'll demonstrate both IPv4 and IPv6 connectivity through our topology. Let's get started. There are a couple of tricks you can use to make your experience better when using Kali Linux on Viral. To start, when you download the image from the Offensive Security website, it's in VMware VMDK format. Viral can convert it to the native OpenStack format for you, but before you install in Viral, you'll want to add any additional software that you might need, most notably Cloud Init. This will automate the IP addressing configuration for your VM. In User Resource Manager, under Node Resources, you can add your Kali image to Viral. For ease of use, name your image Kali. Although Viral already has configurations for Kali, you'll want to make sure that the hardware video model is set to VGA and the hardware disk bus is set to SCSI so the system boots properly. Here is our topology, which I've already laid out. We have a Kali Linux machine on the left, and then on the right we have an Ubuntu server. Each is connected to their own layer 2 switch running iOS. In the middle of our network, we have a partial mesh of 4 routers. To automatically configure our internetwork with AutoNetKit, we'll configure our management network to private simulation network and use an LXC management node. We'll configure Cisco Discovery Protocol to true so that we see our neighbors, and set the IP address family to dual stack. This will configure both IPv4 and IPv6 for us. The IPv4 infrastructure subnet will be used for the point-to-point links between nodes. We're using 10.0.0.0. The loopback subnet will be 192.168.0.0, and the VRF subnet will not be used. We also have the same subnets for IPv6 infrastructure and loopbacks, set as shown here. We'll make sure our interior gateway protocols are enabled and set to open shortest path first. Both OSPF version 2 for IPv4 and OSPF version 3 for IPv6 will be configured. Now we'll generate our initial configurations to push to the devices. We'd like to see the configurations generated, so we'll click Yes. You can navigate to each device configuration by clicking on the special scroll bar on the right-hand side of the window. You'll see that not only do we have router and switch configurations, but we also have our host configurations in Cloud Init format as well. If there are any questions about what usernames and passwords to use, make sure you take a look here. We'll choose No for Auto Netkit visualization. This is a useful feature to browse through your network and automatically generate a network drawing for future reference. You'll see that all of our routers now have v4 and v6 addresses. These are their loopback interfaces. Let's go ahead and start the simulation. I'm going to go ahead and log into my Kali Linux machine. Now, I've customized my environment before installing Enviral, so I'm using the XFCE environment rather than GNOME, so my desktop may look a little bit different from yours. Let's take a look at my machine's IP address configuration. You'll see my management network on Ethernet 0 and my network-facing interface on Ethernet 1. I have a v4 address on both interfaces, but you'll note that Ethernet 1 has both a v4 and a v6 configuration. Let's use the telnet command to log into the router. Username is Cisco and password is Cisco. We'll look at the routing table. You'll see that we have all of our routes and OSPF is fully adjacent and converged. The 10.0.0.8 subnet connects to the Ubuntu server. AutoNetkit tries to conserve as much address space as it can and allocate subnets with the prefix length only enough to give all the hosts on each link an address. I'll ping the router that is connected to the server at 10.0.0.9. Then we'll log out and trace route to that IP from Kali. You can see the intermediate routers and their IP addresses. Now if we trace route to 10.0.0.10, you'll see that we reach our server. Note that the path to the server is different from the path to the router. This is because one of the routers in the path is load balancing using equal cost multipath or ECMP. Router iOS v1 has multiple next hops to the 10.0.0.8 subnet. Let's look at the routing table for the Kali host. Viral has already set up static routes to the subnets in my routed network. It has also done this for IPv6 as well. Using copy and paste for the lengthy v6 address, I'll use traceroute over IPv6 to my server and the last hop router. You'll notice that the path to the server and the router are different. Again, this is because of equal cost multipath. This concludes this demo of using Viral to simulate an internetwork with hosts, routers, and switches. Thank you for watching.